All right, and we're live. Here's the promised blue glow that I was reminding you about from the Crab Nebula. There it is, right there, the synchrotron radiation coming from the nebula. Synchrotron radiation is polarized, and that allows us to use it to study the magnetic field. In other words, here's all the stuff about flux freezing. In other words, the radiation has its electric field preferentially perpendicular to the magnetic field lines, and its magnetic field is preferentially along the magnetic field lines. So by using polarizing filters, we can exploit the fact that the radiation is polarized, is primarily having its electric field vibrating, if you will, along a direction determined by the local magnetic field line. So that means that if you put a polarizing filter in front of it, the brightness varies, and how it varies from location to location within the nebula, depending on the local orientation of the magnetic field. So you can study the orientation of the magnetic field by studying the polarization of the radiation. This is illustrating both the headlight effect and the idea of an electron spiraling around the magnetic field line, primarily emitting in the forward direction, and the photons are polarized like such. So, you guys familiar with polarization? Mm-hmm. No, okay, just checking on that. Yeah, okay. Okay, so we're going to talk about the emission what I'm going to say, how the pulsar spins down, how it loses energy. So hold this thought. I guess I'm not ready to talk about it yet. I was thinking, do I want to do that? Now I'm thinking, no, there's a little bit more I want to write here, and then we'll get to that. So, you guys, change the perspective of our viewer at home. Yes, our hypothetical Diego at home.
This lecture's mentioned viewers like you.
Yes.
Watch what you say there with you with copyright issues.
PBS is going to come for us.
Did you use our slogans?
So regarding the pulses, we still don't know exactly how the pulses work. The exact pulse mechanism is not well understood. Electric fields generated by the rapidly changing magnetic field at the surface of the spinning pulsar. You can estimate they'd be on the order of about 50 billion volts per meter. That's pretty good. Intense E fields generated at the neutron star surface by the rapidly changing magnetic field of the pulsar, of the spinning pulsar. this. Oh no. What am I gonna do? I'm going to grab another piece of chalk. That was close.
That could have been a disaster.
It could have been, that's right. I wouldn't have known what to do. On the order of 5 times 10 to the 10 volts per meter! Exclamation point. So there's my rapidly spinning neutron star. Remember Faraday's law. E is minus, curl E is minus dV dt as well. Curl E is minus dV dt. In other words, a changing magnetic field gives rise, a time variable magnetic field gives rise to an electric field, is what Faraday's law says. Well, if I'm at any given location, hovering above the surface of the neutron star, as that thing spins around, the magnetic field at any given location above the surface is very rapidly changing. So dV dt is huge, so curl E is huge, so E is huge. That's what it comes down to. There's a rapidly varying large electric field associated with the rapidly varying magnetic field at the surface. In the lab frame where the pulsar is spinning, right? In other words, I'm not saying follow the rotation of the star around. I'm saying if we're in the lab frame, if you will, hovering above the surface, the magnetic field at that point in space is very rapidly changing. And even though the gravity of the neutron star is incredibly strong, an electric field that large is enough to rip protons and electrons out of the neutron star's surface and send them moving along the magnetic field lines. So this would alternately rip electrons and protons out of the crust and inject them into beams along the magnetic axis. provided with enough energy, can create electron-positron pairs and the E plus and E minus created that way, they can keep emitting more photons, so you can get a cascading effect. Because those photons could then turn into electron-positron pairs, which emit more photons that turn into more electron-positron pairs. And bunches created like that could produce what we call subpulses. In other words, when you look at the pulse shapes, often there are a number of bumps inside the pulse that could be associated with bunches of particles traveling along the axis. All right, so now let's talk about the light cylinder, this figure right here from your book. So imagine this is a spinning pulsar, rapidly spinning neutron star, and we've drawn a simple dipole magnetic field there. Neutron stars spin very rapidly. So there will be a radius beyond which the magnetic pattern, if you will, like if there was, I suppose that there was a particle spiraling around the magnetic field line here. If you're out past a certain radius, this pattern locally would be moving faster than the speed of light. That's what it comes down to, right? In other words, I can't show it here, but here's me spinning, right? If I'm spinning around, well, if I were spinning fast enough, I would eventually get to the point where my hands were going faster than the speed of light, even if my shoulders were not. Now, I cannot do that, but there would be a point where my hands would be going faster than the speed of light, even though my shoulders were not. Which means I literally couldn't do that, even in principle, right? In other words, I could not spin rapidly enough to get my hands going faster than the speed of light because of relativity. And the same thing applies here. The light cylinder is the radius of a cylinder surrounding the rotation axis, such that anything co-rotating with the pulsar would have to be moving faster than the speed of light beyond that radius. That's what is meant by the light cylinder. Okay, any questions? So, what's the significance of that? So, the light cylinder. Cylindrical surface surrounding rotation axis. Such that anything beyond it, co-rotating with the pulsar, would be moving faster than light. Inside the light cylinder, the magnetic field rotates roughly as a rigid body. Light cylinder, the induced electric and magnetic fields are carried away in the form of what is called magnetic dipole radiation, radiated away. Powering the nebula and bleeding off the neutron star's rotational energy. In other words, the magnetic dipole radiation generated beyond the light cylinder is associated with the spinning down of the neutron stars, losing energy. Its rotational energy is being used to power this magnetic dipole radiation. And it turns out that for magnetic dipole radiation, dE dt, where E is the energy, not the electric field, dE dt works out to be minus 32 pi to the 5th power, B squared, R to the 6th, sine squared theta, divided by 3 mu naught C cubed P to the 4th power, where here B is the field strength at the pole, at the magnetic pole, at radius r. So R being, now I can't remember, I can't remember if this R stands for the radius of the light cylinder or the radius of the neutron star, honestly, because I didn't write that here.
Cylinder, because they say R sub C there.
Yeah, the R sub C is for the radius of the light cylinder, right? So it's probably the light cylinder radius, but I can't swear to it. I have to check in the book. Yeah, I honestly don't remember. E is the period. Theta is the angle between the rotation and magnetic poles. So what will produce more radiation if the magnetic axis is more or less aligned with the rotation axis? When would this go to zero? What theta would make this be zero?
When it's
Zero.
aligned with it.
Zero would make it zero. What would that correspond to then? How would the magnetic axis and the rotation axis be oriented relative to one another?
If they were aligned.
They would be lined up in that case, yeah. So that would make it not radiate, because in that case, if it were perfectly symmetric, the magnetic field wouldn't change as the star was rotating, and so you wouldn't have this effect of generating electric fields and getting electromagnetic radiation, essentially. So the more tipped the magnetic field is relative to the rotation axis, the more radiation you get from this phenomenon. Phenomenon. Yes.
My own little world over here.
Yeah, pretty much, yeah. Doesn't there, sure.
Derek was going for a little bit. You just didn't hear it. It was good.
Yeah, it's in his head.
So let's assume that the energy radiated comes from the pulsar's rotational kinetic energy. So remember, just like kinetic energy is 1/2 mv squared, but if you switch to a rotation, m becomes the moment of inertia, v becomes the angular velocity. So the kinetic energy is 1/2 I omega squared. Remember that omega is 2 pi divided by the period. So in other words, the kinetic energy can also be written as 2 pi squared times the moment of inertia divided by the period squared. So then the rate of change of the kinetic energy comes from differentiating this expression. So that gives you minus 4 pi squared I p dot over p cubed, right? Because we're looking for ddt of 1 over p squared here. In other words, the moment of inertia didn't change change because the size of the star isn't changing. And so if I take the derivative of p to the minus 2, that's minus 2 p to the minus 3 dp dt. So you get minus 2 p dot over p cubed, which is exactly what we have over there. 2 times 2 gives us a 4. 2 pi. And that's supposed to be equal to the rate at which energy is being emitted via magnetic dipole radiation. So you set those things equal, equals minus 32 I to the 5th b squared r to the 6th sine squared theta over 3 mu naught c cubed e to the 4th power we can use that to solve for what magnetic field strength is necessary to account for the observed rate of spin down, in other words. So B, if I solve, is 1 over 2 pi r cubed sine theta square root of 3 mu naught c squared c cubed I p dot over 2 pi. Your book does an example, 16.7.2 for the Kraft pulsar. P is a 30th of a second, and it really is a 30th of a second essentially. So, it's 0.0333 seconds. It really is about 1/30th of a second almost exactly. The Kraft pulsar P dot is measured as 4.21 times 10 to the minus 13. So it's slowing down faster than a typical pulsar does, but that's because it's spinning faster, and so it's emitting more radiation. If theta equals 90 degrees, which it pretty much needs to be in order for us to have both beams sweeping past us like they do, then that gives B being 8 times 10 to the 8th Teslas. 800 million Tesla. That's an overestimate because dust and gas in the nebula also exert torques that are slowing the pulsar down. We don't need quite that strong a field to account for the rate at which it's spinning down. Accepted value is is half that. 400 million Tesla for the strength of the magnetic field. Still no slouch. There's another example for PSR 1937 plus 214. There the period is much shorter, 0.00156 seconds. That's a millisecond pulsar. P dot for millisecond pulsars tends to be very small. 1.05 times 10 to the minus 19th power. Millisecond pulsars slow down their spin rates much more slowly than other pulsars do. And that's a clue that they're actually old. They're not young pulsars, they're old pulsars, which at first is kind of mysterious. Wait, don't pulsars slow down with time? Then why are these millisecond pulsars supposed to be old pulsars? And again, the answer is that they appear to have been spun up again by mass spilling onto them from a companion and transferring angular momentum to them. So they get respun. If we put in those numbers, we find its magnetic field is only 8.6 times 10 to the 4 Tesla, which is consistent with the idea that it's an old pulsar that lost a lot of its initial magnetic field strength. It's an old neutron star. So the millisecond pulsars, as we'll talk about more, presumably stopped being pulsars because they're old pulsars for a while, but then they got a rebirth, so to speak. Okay, any questions?
So is it that the dust and the gas are kind of like friction against its spinning?
Yeah, they're helping to slow it down. They also are slowing it down. And so, in other words, it's not just the magnetic dipole radiation that is slowing it down. And so that means that we don't need quite a strong magnetic field to account for the observed rate of spin down. It doesn't have to be emitting as much as would otherwise have to slow down by that much. So this is old data from the 1970s of a so-called glitch in the period of the Vela pulsar. So this is period versus time. And then May, June, July, August, September, October, blah, blah, so months in 75 and 76. What's that?
Much adjacent.
Yeah, yeah. Much adjacent, much adjacent. I never noticed that before. Right. Anyway, so it was happily increasing its period with time, just as we expect, because they are spinning down. But then, all of a sudden, boom, the period shortened, and then it proceeded to slow it down again. So a shortening of the period like that is known as a glitch, and it's a pretty typical phenomenon that every once in a while a pulsar will exhibit a glitch. And so what is a glitch? So there was an old model that they would do to star quakes. So the idea is that the neutron star is spinning very rapidly. It's got this crust made of iron nuclei on it. And since it's spinning so rapidly, there would be a tremendous amount of stress on the crust. So it ought to be possible to have something analogous to an earthquake on Earth, where stress builds up, and then there's essentially a sudden shift in the crust. The idea was that stress builds up on the rapidly rotating crust of the neutron star, and eventually it's released in a starquake that changes the moment of inertia and causes it to spin up. In other words, it would relax and shrink a little bit, and then so that would be by angular momentum conservation, it had to rotate faster. and then it would proceed again to slow down, blah, 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 blah. But if that's not weird enough, the modern point of view is even stranger. So remember that we have those, the interior of the neutron star contains a superfluid of neutrons and protons. And the idea there is, remember the superfluid flows without viscosity. And so you can have a vortex, a whirlpool in it, if you will. You know, what's called a line vortex is basically like a cylindrical flow centered on a line that is a vortex within the fluid. A superfluid, the vortex can spin forever. Okay, so that would be the idea. And the idea, though, is you got these vortices, you got these vortices in the superfluid that get attached to the crust on one end. And as the neutron star spins down, then the rate at which the crust is spinning is systematically becoming less than the rate at which the vortices are spinning. And that would build up stress. And that what would happen is that eventually the vortex would detach from the crust and produce a sharp jolt that then produces the glitch. Okay, that's weird, but that's the current picture, is that they're caused by detachments of superfluid vortices from the crust of the neutron star. Well, okay then. So let's write that down too, shall we? Sure, let's do it.
Woo.
Woo.
Dr. Harmon and Alex is throwing things at me.
Oh man.
I need you to turn this card over.
It's fine. Here's my.
All right, I guess I just, here, I'm just be zoomed in on you two so I can get. I
Review
can
the
get
tapes.
Yes, that's right, yes, I can review the tapes. Yeah.
As you can clearly see.
By the way, viewer at home, here's that glitch that I was talking about but not showing to you. But I'm sure that you were looking at the notes and you were seeing it anyway. But, yeah, so, all right, you two, you behave yourselves. Oh, look at this innocent face right here.
Oh, wait, there's a third.
I never heard him before. Wait, is that you? We should get those cards like when you were in like 3rd grade and everyone had like a card with their name. And so like when they did something wrong, they got like a different colored card.
We didn't do that.
You didn't?
No. That's because when I was growing up, kids were well behaved.
Ah, yes. Those damn millennials as children.
That's why it never happened that on my high school's class T-shirt that one of the names is actually a 30-year-old police narc who was sent in order to combat the drug problem that we had. That would have never happened.
That would never happen.
That's ridiculous.
No.
Yeah.
We lived in the good old days.
Yes. There's no fake person whose name was Tony Houston on those shirts.
That's actually hilarious.
And it certainly didn't happen that being the sort of friendly person I was, I wanted to introduce myself to the new kid. And so I asked him where he was from and so on and so forth, trying to be friendly. And then he asked me if I knew where he could buy drugs.
That's a pretty forward narrative. I don't know if you did a very good job.
Welcome to Cincinnati.
The fact that he didn't manage to put it together.
This really nice kid probably has drugs.
Yeah. Well, at that point I decided he's not in the crowd. He said he had to talk to somebody else to figure that out. And so as a result, I'm not one of the people that was talked to by the police not long after. So anyway,
It's very funny. This is why you can't be nice to anyone.
bitch.
The late 1900s, simpler time.
The late 1800s.
19.
Right.
That's the late 1800s.
No.
I'm not confirming that old.
Thanks.
Were you there when they made the Constitution?
Who was Benjamin Franklin?
I was a
I
professional aggressor.
tried to keep out the Second Amendment, but I was outvoted.
Yeah. No, it's that.
Old model was a star quake due to stress built up in the crust as the neutron star spins down, and so as a result that would cause the shape of the crust to keep changing, and that would build a stress in it. Because the faster it's spinning, the more the star would tend to bulge at its equator. So as it's slowing down, the shape, the equilibrium shape would change, and so that would build up stress, and it would eventually be released as a star quake. That's easier to understand. So it's too bad that doesn't seem to be raised. It builds up in the crust as its shape changes due to spin down. New, totally freaking weird model. As crust slows down relative to superfluid vortices attached to it, they stretch out. When the tension becomes too great, they detach and deliver a sharp jolt. All right, then we'll finish neutron stars. So next week we can start doing general relativity and black holes.
Woo!
We'll finish neutron stars here.
Yeah.
What's that?
Surprised we're getting to our exam. Yeah.
Yeah.
Sunset?
On Tuesday. is it?
Tuesday.
Ooh.
Last I checked.
Tuesday.
Tuesday.
Okay.
Saturday.
No, it'll be a glorious.
We should call it Wednesdays
The
for
week
days.
after that's the side week.
Or for you at least. The linear algebra thing.
Linear, thermal, and 2 days of initiation.
Wow.
Same days.
I'll pray for you.
So-
No, I won't actually. I love making jokes about things that I do on religious holidays. Like I never do work on the Sabbath.
It's okay.
It's the Lord's Day. I can't.
There you go. Yes, you feel very strongly about
Exactly. I can't
it.
do
It's
it.
very, very noble. All right, so here we go.
In that case, the Lord stays the entire weekend.
Okay, here we have a globular cluster. Globular clusters are very old. If you look at their turning points off their HR diagrams, they're billions of years old. And so they should contain old neutron stars because of the fact that they're billions of years old. So they should have old neutron stars left over from supernovae that happened billions of years ago. These are common sites of so-called millisecond pulsars. So, how are millisecond pulsars formed? Well, Scott Ransom at the National Radio Astronomy Observatory produced this helpful scenario thing for us, basically, this slide. So, the standard scenario, 1 to 4, a massive supergiant star and a normal sun-like star orbit each other in a binary star system. The massive star exhausts its nuclear fuel and explodes in a supernova, leaving a neutron star as its remnant. For several tens of millions of years, that neutron star is likely active as a radio pulsar. Remember, we said that the real lifetime, based on P dot over P, was a P over P dot was on the order of a few tens of millions of years. Eventually, it slows down, turns off as a pulsar, and becomes simply a cooling neutron star. But 3 after billions of years, and if the binary survive the supernova, the lower mass star evolves and expands into a red giant. Material from the star spills into a disk around the neutron star and eventually onto the neutron star surface in a process known as accretion. Accretion transfers angular momentum to the neutron star and makes it spin more rapidly. During this process, the system is visible as an X-ray binary. And that's because material accreting on the neutron star surface actually undergoes nuclear fusion and emits bursts of X-rays as a result of that. Once accretion ends, the neutron star is spinning very rapidly and emerges as a millisecond radio pulsar. This process is known as recycling. Strong winds from the pulsar slowly erode away the companion star, which can eclipse the pulsar's radio emission. So that's the standard kind of scenario for making millisecond pulsars, is that it's actually a very old neutron star, which gets spun up again by accretion from the companion star, spins it up so that it's spinning fast enough to once again be a pulsar. But in a globular cluster, figure 2, there are so many stars packed so densely together that interactions between ancient dead neutron stars and normal stellar binaries can occur. So in a globular cluster in the center, instead of the stars being light years apart, they're typically like weeks apart. If you were in the middle of a globular cluster, the entire sky would be filled with stars that were brighter than the planet Venus. It would be spectacular to view because they're so, in stellar terms, tightly packed together. When this happens, in a process called exchange, the lowest mass star is usually ejected from the binary and the neutron star replaces it. So it's kind of like the neutron star is this obnoxious person that, takes away your dance partner, right?
And kills it.
And kills it. Wait. Wow. No, the dance partner just leaves, still alive. Yeah. Well, okay. Once the remaining normal star evolves into a red giant, the rest of the standard recycling scenario takes place. These interactions and exchanges explain why globular clusters have so many more millisecond pulsars per unit of mass than the galactic disk. Millisecond pulsars are particularly common in globular clusters, more so than you would just expect from the number of binaries you would think would be there, and this scenario would give an explanation for that. So millisecond pulsars are old neutron stars that got spun up by transfer of mass from a companion, is what it comes down to. Yes?
So during that process in the globular cluster, what would happen to all the planets that were around orbiting, say, that star?
So a binary star system, it's hard to get planets to be in stable orbits around it to begin with. Tatooine would not work. Because if you were close enough to a pair of sun-like stars like that, you wouldn't be in a nice stable orbit. You'd have to be further away from them, I think. There is some evidence for planets in binary star systems, but an Earth-type planet orbiting a double sun would not be a stable configuration. But in any case, I don't know what would happen if there were planets. I don't know. They'd very likely, I think, get ejected out of the system. If there was any planets anywhere close in, they'd probably get kicked out of the system by the strong gravity of the neutron star. But that's just my guess. Any other questions? All right. And exciting. General relativity next. Woo! Woo! And an exam. No, woo! Wow.
The orb of confusion is coming.
You could say it'd be cool to have it be a globular cluster where there's a bunch of suns in the sky, but then you couldn't look at the sky because every part would burn your eyes.
Well, no, they would just be very bright. I don't think it would actually burn your eyes.